The electrical force, also called the Coulomb force, is really strong. If you have two charges, positive and negative, they'll be attracted to one another. Let's compare the Coulomb force to the force of gravity. It turns out that both of these forces are inverse square forces, meaning that the strength of the force depends on the distance between the two objects. Neither of these are approximations, by the way, is correct in certain extreme environments. Newtonian gravity is not really accurate near the edge of a black hole. For instance, you need general relativity to make proper predictions. And the Coulomb force is kind of an approximation to quantum electrodynamics. But for the kinds of forces that we're familiar with on a day-to-day basis, these simple formulas here are highly accurate. What I'd like you to do is compare the constants. So let's first look at the gravitational constant g. It's got 10 to the minus 11 power in SI units. But the Coulomb constant is 10 to the positive 9th power. We have 20 orders of magnitude difference between these two forces, and you've probably noticed this in your daily life. A tiny kitchen magnet stuck to the side of a refrigerator can overcome the entire gravitational attraction of the whole Earth because the magnet sticks to the refrigerator rather than fall to the ground. Just a few properly placed electrons in the magnet are all that are needed to overcome the gravitational force of the Earth. So it's very interesting that both of these forces happen to follow inverse square laws, because this directly results in orbits that are stable. In the case of the Moon orbiting the Earth, for example, the orbit has been stable for eons. The Moon doesn't really spiral down or spiral up due to gravity, and its orbit is pretty much periodic, with a rate of repetition of 1 revolution per month. This same stability holds the solar system together and holds the Milky Way galaxy together too. When we then think about the Coulomb force, this inverse square law is also responsible, in a way, for the stability of electron orbits around atomic nuclei in atoms. There's some very interesting mathematical theorems where people have considered hypothetically what would happen if the gravitational force were not an inverse square law? What if the Coulomb force were not an inverse square law? What if it had some other formula where it wasn't r squared in the denominator? It turns out that there are only two forms of forces that give you stable orbits. One is called the harmonic oscillator, and one is the inverse square law. Only two. It's very nice that our universe produces stable orbits, because otherwise all interacting objects would either spiral towards or away from one another. Orbits would certainly not be circular in such a hypothetical universe. It's interesting because I just mentioned that Newtonian gravitation is only an approximation to the more accurate general relativity. So what this actually means is that in reality, gravitational orbits are a little bit unstable and do indeed decay over time, but only a little bit and very, very slowly, fortunately. Because the Coulomb and gravitational forces have the same mathematical form, let's talk about atomic binding energy by considering first the motion of planets around the Sun. Now we know that electrons are not actually little spheres in orbit. It's a little bit more complicated than that. But if we're going to compare Newtonian gravity to the Coulomb force, then it's a suitable comparison because mathematically these two formulas are the same. Let's take a look at a toy model of Earth and Venus in orbit around the Sun. Now, obviously, this is not to scale, but we're going to simulate Newtonian gravity accurately. I picked these two planets, Earth and Venus, because they have very similar sizes and similar masses. The mass of the Sun is 10 to power 30 kilograms, and you might notice that Earth is orbiting a little bit further out than Venus. Earth orbits 149 million kilometers from the Sun, and Venus at 108 million kilometers. Therefore, Venus is orbiting a little bit faster, so it doesn't fall down into the Sun. Both of the planets have nearly stable circular orbits. I like to think about gravity as being warped space. So if you imagine a two-dimensional situation rather than a three-dimensional one, you can think about a giant stretched piece of fabric with the sun weighing down the fabric in the middle. If I then imagine a planet as being a little marble rolling around on that fabric, if I have the fabric shaped exactly the right way, then I should be able to reproduce what gravitational orbits would look like from above by rolling a marble on the fabric and seeing where they go. So the stretched shape you're seeing here has been calculated to give exactly the right curvature so that objects rolling around on it would produce paths that are identical to paths they would take if they followed the rules of Newtonian gravity. Let's now animate the movements of Venus and Earth around the Sun. Venus is a little bit closer to the Sun than Earth, or equivalently, you can say that it sits deeper within the Sun's gravity well. You might notice that Venus is orbiting the Sun faster than the Earth is. The orbits are periodic and more or less circular. I have a good reason to show you this model because we can learn something very interesting about solids, and that's the following. In the simulation, both the Earth and Venus are bound to the Sun. I mean, their orbits are nice, beautiful circles. Neither planet will deviate much from their circular orbits and fly out of the solar system away from the Sun. They don't spiral down and crash into the Sun either. And that's what's very nice about Newtonian gravity. In simple systems, orbits are stable, thank goodness. But let's say that hypothetically, we want to eject the Earth from the solar system so that it would exit its stable orbit and never come back to the solar system after that. How much extra kinetic energy would we need to give the Earth for that to happen? It turns out that we would have to impart to the Earth an additional kinetic energy of 2.6 times 10 to the power 33 joules. But for Venus, we would have to give it a little more because it's starting off in a lower orbit. In other words, for a planet that orbits closer to a star, if it's roughly the same mass as another planet orbiting further away, you would have to give it comparatively more energy if you want to tear it away from the star it's bound to. And I hope that you can appreciate that the same thing must be true for electrons in orbit around atomic nuclei as well. Electrons that are orbiting far away from their atomic nuclei are easier to strip away than those electrons which are orbiting close to their atomic nuclei. In the calculation here, what I've done is to start off with the velocities that the Earth and Venus currently have in their orbits. And then I compared these numbers to the escape velocity, and I calculated the required change in kinetic energy to alter the velocity using the well-known formula delta E equals the difference of 1/2 mv squared, where m is the unchanged mass, and we have the final and initial velocities v. By the way, you might be used to the units of joules to express energy. Quite often, we use a different unit, the electron volt, which is also a unit of energy. 1 electron volt is the energy you need to move 1 electron through a 1 volt potential. It's the definition of an electron volt. This is a graph of the stretched fabric solar system showing the Earth and Venus in their orbits with the Sun in the middle. What I've labeled here is the escape energy. How much energy would we need to give the Earth for it to escape the solar system is indicated by the distance between the arrows, and how much energy we would need to give Venus in order for it to escape away from the Sun from its orbit is also indicated. Obviously, Venus needs more energy if you're going to knock it out of its orbit than the Earth does because it starts off deeper in the Sun's gravity well. This is analogous to the situation of an electron in orbit around an atomic nucleus. It's easier to strip off outer electrons that orbit farther away from the atomic nuclei than it is to strip off core electrons, which orbit more closely. Now, looking at the stretched fabric system from a slightly different angle now, let's consider what would happen if, hypothetically, we had another star passing through the solar system. Would this affect the orbit of the planet? It's easier to talk about a slightly simpler scenario. If we suddenly had another sun pop right up next to the one that we already have, how would the orbit of the Earth be modified? Now, this is, of course, the famous three-body problem. It turns out not to have any analytical solution. mathematicians have fretted over this problem for decades before somebody finally discovered that there is no solution. And when I say no solution, I mean there's no analytical solution or no solution that you can write down with a formula. You can always solve the problem numerically, though, and that's what I've done in the next simulation. So let's assume that we have the Earth and Venus in their happy circular orbits, and suddenly another sun pops up into existence in the solar system. Let's play this simulation. So Venus is still orbiting the sun. Unfortunately for the Earth, it's now on the move towards the other sun. And if you look at Venus, it's actually not in quite the same circular orbit it was before. Its orbit has been modified a little bit. It's chaotic. And here's the point that I want to make. This is kind of what happens to electrons moving around in molecules with covalent bonds. For example, diatomic molecules like N2 or O2, nitrogen or oxygen gas. When you put two atomic nuclei nearby one another, the core electrons will stay bound to just one atom's nucleus. And all of the electrons will stay bound to the system as a whole, just like in the situation shown here with two stars. Both Venus and Earth stay in some kind of orbit around the two-star system as a whole. But the more loosely bound orbits are modified more when the system is disturbed. Let's now take a look at an even more complicated situation. What if we had 16 suns? Now it's going to be kind of hard here in the next simulation to keep track of the Earth. I'm not going to show Venus in the animation because Venus always stays bound to just one sun in this setup. I'm only going to show the Earth, and you need to look closely to keep track of it. So there it goes. Earth is shooting out on that star. It's moving all over the place, though. It's clear that the Earth is not going to exit the 16-sun system as a whole. It's not going to become unbound to the system and just fly off the edge of the fabric. But it does migrate all over the place within the 16-sun system, from sun to sun in a somewhat chaotic way. And this is a single energy orbit. After the Earth was launched, no extra kinetic energy was added to the Earth externally. It's just falling around the system due to gravity. It just has one energy. Let's now imagine that these suns represent atomic nuclei, and the little Earth is an electron moving around. Then this is kind of what happens in solid crystals, where you have many evenly spaced atomic nuclei. In solids, the inner electrons, corresponding to Venus, each stay bound to a single atomic nucleus. They don't go anywhere, but when you have a lot of other atomic nuclei nearby, and some of the more loosely bound electrons might start to roam around all over the crystal, just like what we've seen here with a single Earth roaming around a 16-sun gravitational system. Now this is a plot of the orbits and the three systems we just simulated, looking down from above. And as I mentioned before, the stretched fabric model of the gravitational force means that these plots of the orbital trajectories are accurate, as if the little Earth or Venus were in free space orbiting under gravity rather than rolling around on a frictionless piece of fabric. So if you only have one sun, you get nice circular orbits for both Earth and Venus. If you have two suns, and they're the right distance apart, you will get kind of a nice figure 8 orbit for the Earth. Venus has a kind of slightly chaotic orbit, but anyway, it's still bound to a single sun. If you have 16 suns, Venus's orbit is still bound, but look at the Earth. You can see that it's moving all over the place. So Venus kind of represents those electrons in a solid, which are each bound to their own little atomic nucleus. And the Earth, in this analogy, kind of represents those electrons where they are more loosely bound and can participate in electrical conduction as they're free to move around the crystal or to move from atom to atom inside the crystal. Now, this certainly isn't true in every solid. It's not true in solid sodium chloride salt, for example, because it's not conductor, but it's true in metals. And even in this 16-sun analogy, the Earth is still bound to the system as a whole. It's just free to move around, but it doesn't exit the system. Analogously, if you have a block of metal, electrons are not just going to suddenly leap off of the surface of the metal without extra energy. You have a lot of free electrons moving around inside of a piece of metal, but they don't just suddenly exit to the air unless you do something. Here are the key learning points for this video. Firstly, in an atom, it's those loosely bound outer electrons that are easiest to strip away. Secondly, in solids, you have some inner electrons which stay close to the nuclei and remain bound. And you have some further away that roam around the crystal. This is true in metals, but not in insulators. Therefore, thirdly, ionic solids tend to be very good insulators. But when you put them in solution or you melt them, it's the ions, positive or negative, that can conduct electricity because they move between the electrodes. And finally, anytime you have electrons, if you put enough of a potential difference, or in other words, a high enough voltage around them or across them, you can get those electrons to conduct electricity. And we'll see more of that in part 5.